In this video we're going to have a recap on the binomial distribution, and we're going to do that by having a look at a simple example. I'm just going to be taking a die and I'm going to be rolling it a number of times, and I'm going to be interested in the number of times that the number 6 crops up. Let's start off by having a think about what happens if I roll it once. So to roll it the first time, my probability of success, my probability of getting a number 6 is just 1 chance in 6, assuming that I've got a fair die. My probability of failure, probability of getting anything other than a 6, is going to be 1 minus a 6, which is 5, 6. So I've got a 5, 6 probability of getting a 1, 2, 3, 4, or 5. So if I roll it once, I've got a discrete, because I've only got 6 possible outcomes, uniform distribution. But rather than rolling it once, I'm going to roll it a number of times, and I'm going to pick the number n equal to 6. So I'm going to roll my dice 6 times. And I'm going to end up with a binomial distribution. So I'm going to roll it 6 times, and I'm going to define a variable capital X equal to the number of times I get a 6. So I've defined my variable, number of times I get a 6 when I roll my dice 6 times. Well, X could take the possible values. I could be really unlucky and get no 6s out of the 6 rolls. So 0 is a possibility. I could get 1 6, I could get 2 6s, all of the way up to 6. So if I'm rolling my dice 6 times, I can't get more than 6 6s. So X itself is a discrete variable. It can only take the values, 7 possible values, 0, and then 1 through to 6. And I can work out the probability that X has each of those values. So if I start off by having a look at the probability that X is equal to 0. So that's the probability I get no 6s when I roll my dice 6 times. So the first time I roll that dice, I need to be unlucky. And then when I roll it for the second time, I need to be unlucky again. And then the third time, I still need to be unlucky. Then all the way through, up until the 6th roll, I need to be unlucky again. So this is equal to 5 6 to the power of 6. I've got 6 rolls. Each of those rolls are independent, so I can multiply the probability of failure together, and I'm going to get 5 6 to the power of 6. So I can pop that into my calculator, 5 divided by 6 to the power of 6, and I get the value 0.335. So 33.5% of the time, when I roll 6 dice, I expect to get no 6s. Okay, let's have a look at the probability that X is equal to 1. So out of my 6 rolls, one of them will be, exactly one of them, will be a number 6. So in that case, let's have a think about what happens if I'm successful on the first roll. So the chances of that happening is 1 in 6. And then I need to be unsuccessful, I need to fail in the next 5 rolls. So I've got 1 trial I'm successful, 5 rolls I'm unsuccessful, and I've got, if I add those two together, 1 plus 5, I've got my 6, I write my 1 in, I've got my 6 trials I've completed, and I can also put that into my calculator. Before I do that though, what I've thought about so far is I've come up with the probability of being successful and then failing 5 times. But I could also have failed the first time, then been successful, and then failed for the next 4. Or I could have failed for the first 2, then passed, then failed for the next 3. So I look at those possible combinations. I've actually got 6 possible combinations, and they're the different rolls. So I could have been successful on the first roll, second, third, fourth, fifth, and 6th. 6 possible combinations. They're all equally likely to occur with this probability. So 1 6 times my 5 failures, so 5 6 to the power of 5. So the total probability of getting 1 6 is going to be equal to my 1 6 to the power of 1 times my 5 6 to the power of 5 times the number of possible combinations, which is 6. That I can now put into my calculator. So I've got 1 divided by 6, and I'm going to multiply it by 5 sixths to the power of 5, and then I'm going to multiply it by 6. And I get the value 0.402. So that's telling me if I roll 6 dice, 40% of the time I expect to get exactly 1 6 out of the 6 rolls. Let's have a look at probability that x is equal to 2. So it's a similar idea. This time though, we need to be successful twice, and we're going to need to be unsuccessful 4 times. So again, the powers 2 plus 4 is going to add back to my total number of trials, which is 6. I've got 2 successes and I've got 4 failures. But I also need to think about what the combinations are, the number of possible combinations of being successful, of where those successes occur out of the 6 rolls. So I need to multiply it by 6 choose 2. So I've got 6 possible, my 6 rolls, and I've got my 2 successes that I can distribute anywhere amongst those 6 rolls. The number of combinations is going to be 6 choose 2. Hopefully this is familiar from all the work that you've done in terms of binomial expansion. It comes out of the Pascal's triangle. So just a quick reminder, n choose r is equal to n factorial, well, just shift that over a little bit, divided by r factorial times n minus r factorial. So I've got 6 choose 2. So I've got over here, I've got 1 6 to the squared, to the power 2, 5 6 to the power 4, and my 6 choose 2, this is going to be 6 factorial divided by 2 factorial multiplied by 6 take away 2, 4 factorial. I can simplify this down a little bit. Remember that 6 factorial is just equal to 6 times 5 times 4 times 3 times 2 times 1. That's just 4 factorial. And I need to divide it still by 2 times 4 factorial. These cancel. I've got 6 times 5 is 30, divided by 2, that's equal to 15. So this was 6 factorial over 2 factorial, 4 factorial. Number of possible ways of choosing my 2 successes out of the 6 rolls, 15 unique combinations. So this is equal to 1 6 squared times 5 6 to the power 4 multiplied by 15. And pop that into the calculator. That's going to give me 1 divided by 6 to the power of 2 multiplied by 5 divided by 6 to the power of 4 and multiplied by 15, and I've got the value 0.201. So 20% of the time, if I rolled my 6 dice, I would expect to get exactly 2 6s. Now the good news is we can use our calculator to help us do these calculations. Before we do that, I just want to have a think about coming up with a generic value for my value of x. So if I have a look at the probability that x is equal to little r, I'm going to get the probability that I had r successes, so the probability that I get r sixes when I roll it 6 times. So my probability of getting 1 multiplied to the power of r, and then I'm going to multiply that by 5 6 to the power of, in this case, n minus r. So I've got r successes, I must have n minus r failures. So when I add these two powers together, I've got my n trials, my n rolls of the dice. And my n in this case is 6, so I'm going to write 6 in before I completely generalise this expression. So I've got r successes and 6 minus r failures. and then I need to multiply it by the number of different ways that I can choose my R successes out of my 6 R's, my 6 rolls. So that's my probability that X is equal to R with my generic example, with my specific example of rolling my dice and looking at the number of times that 6 is going to occur. I can come up with a more general expression. I can say that the probability that my binomial distribution of X equal to R successes is going to be equal to my probability of success. We've been working with a sixth, but more generally it's P, to the power of R multiplied by my probability of failure raised to the power of the number of trials, take away those number of successes. So again, I've got R, if I add it to n minus R, I've got my n trials. So R successes, n minus R failures, and I need to multiply that by my n, choose R. So if I've got my n trials, I'm looking for the probability that I get R successes. I can put this into my calculator. I know P, I know Q, I know R, and I know N. I can work out my binomial distribution. The good news is my calculator can do it for me. So if I go to my menu and I press 7, and I've got this option number 4 here that says binomial PD. So binomial probability distribution. So if I press that one, I've got the option of listing, so I want you to know multiple values of R. I could go for the list option. I'm just going to look for a single value of X equals 2. So I'm just going to go for the variable number 2. So my value of X I'm looking for, in this case, let's do X equals 2. My number of rolls, well, I was rolling my dice 6 times. My probability of success is 1 divided by 6. Hit my equals, and I've got the value 0.201. My 0.201 that I got from the long-handed method. So it's important that you know how this binomial distribution has been derived. But most of the time when we're looking at these questions, we're going to be using the calculator, and it's going to be doing the hard work for us. So it's important you know where it comes from, but most of the time we will be using this calculator. So we've got the probability that X is equal to 2.